Can you hear me?
Yeah.
Eh, All right, thanks. Minute here. All right, guys. Okay, so get started and do this here. All right, so do you guys have any questions that you'd like to see looked at first? I mean, I can go through uh, the practice. I'm looking at the first practice exam. There's a practice exam 1B as well.
If we just go through it, that'll probably be good. The only things I had real questions about were four because I just the wording seemed too open-ended. And then 5B because it asked about nullity, and I don't think we talked about that.
Yeah, okay, I can explain that that is something that we should talk about. I'm hoping tomorrow. It's on this section. It's not it's essentially, yeah, it's the dimension of the kernel. So this is nullity. Um, but yeah, I think that yeah, that's fair. This is in the section that we're kind of wrapping up. So yeah, I'll talk about it. All right, so I'll go through some of this and then you guys can ask questions. So the first one is sort of a basic functions question, um, asking whether or not you have onto or one-to-one properties. And if you look at this question for F, um, this one thing you might suspect here uh, is that this may have an inverse, and so you could kind of set up an equation like this. This is something sometimes you do in high school, is you try to find an inverse by solving for the other variable. So you can say, okay, well, if I take W minus 4 equals Z bar, and then if you bar a bar, in other words, if you conjugate a conjugate, you can get, you could say that this is G of W, G of W. So what I'm doing is I'm solving for Z in terms of W. And so you can show just through that G is an inverse function. F. Um, and you can just show that directly by composing and seeing you get the identity function. And then knowing, so then you um, if know that G, well, if a function has an inverse if and only if it is a one-to-one correspondence. So then F is a one-to-one correspondence, meaning it's both onto and one-to-one. -one. to one. That's that.
For
Yeah.
that one, I said that Z is because it's complex. I said that Z is A plus BI, and then I just said that Z bar is A minus BI. Um, is
So
that
you did something like F of A plus BI, this kind of thing?
yeah,
A minus BI plus 4.
and then just explained how that is one-to-one correspondence. Is that fine as well?
Yeah, you can do it multiple ways.
Okay.
So there's a lot of ways you can do this problem to show it's a one-to-one correspondence. What I'd like to see though on a problem like this is not just for you to state um, what it is, but also I know that the phrasing is maybe saying, just tell me if it's one-to-one, onto, and so on. But I'd like to see some kind of reasoning behind it if you can provide that. It also asks for the, excuse me, it asks for the range, but if it's a one-to-one correspondence onto, so the um, range is uh, just all of C.
Okay.
So if you write that, I mean, if you said it's a one-to-one correspondence, I may not, even bother thinking about what that is. You know. All right, for B, this is A, here's B. For B, okay, we have a linear transformation, which is given by multiplication by a matrix. So what do I want to say? So, well, you can do a couple of things. You can take this matrix and do row echelon form. And if you do row echelon form, you can do something like I guess R2 minus 2 R1, R3 plus R1. Just doing both operations. I have 1, 3, 0, minus 2, and then 0 something. Also 2 here, right? And then one more, 1, 3, 0, minus 2. Here I'll just add R2 plus R1, 0, 0. Oops, R3 plus R2. Sorry, guys. Plus R2. Get this. This is in row echelon form, not reduced row echelon form, but I don't mind so much. Because it's in row echelon form, yeah, we have this kind of staircase thing. We can see that we can see how many columns are basic versus how many columns are free. No free ones, right? So no free columns. And when you have no free columns, the kernel is 0, which implies kernel is 0. Zero kernel. When you have 0 kernel, it's 1-to-1. That implies T is 1-to-1. On the other hand, this also tells you something that we've learned recently as well, right? Which is the rank. You remember the rank is the dimension of the image. And that's also calculated by what we talked about in class on Monday, by the number of pivots, right? So the rank of T, this is equal to the dimension of the column space T, which is equal to also the image. Sorry, not the column space. T is a linear transformation. This is to say the image of T. Right, the rank of T is what? Two pivots. So this is a two-dimensional. The image is two-dimensional. 2 is less than 3. Yeah, 2 is less than 3, so it's on 2. Or so it's not on 2. Pardon me. So that image, what I'm saying is the image of T is a proper subspace. of the three-dimensional space R3, not on 2. Not on 2. And furthermore, the range, you know what the range is. What is the range here? I mean, just from a description, what's the range of the space? Range is equal to the image when you're talking about linear transformations. But what is the image of a space given by multiplying by a matrix like this? You could say it's a plane, or you could actually be more explicit and say it's the span of the columns. The column space. Span of these two columns. Is it okay? You guys are too shy. You should just shout out if it's okay or if it's not. Is it okay?
Wait, so you said it's 1-to-1, but not a 1-to-1 correspondence?
Not on 2, so it's not a 1-to-1 correspondence.
Okay.
So
Okay.
when a 1-to-1 correspondence must be both on 2 and 1-to-1.
Okay.
So this one's just 1-to-1.
Okay. Thank you.
All right, so that's these two. Likely you'll get one of these, which is like a multiplication by a matrix, right? And I'll ask you to tell me something about it. So you should see, you should try a few different matrices, maybe of different sizes, and kind of try to answer this problem with different sized matrices. But what you need to do is, or what you can do always, is you can do this exercise. Just get a row echelon form, and that will tell you the dimension of the kernel, because that's the number of free variables, and it will, or the Bowden for the language here is the nullity is actually the number of free variables. That's the dimension of the kernel for multiplying by a matrix. And so that nullity is just the dimension is number of free variables, and the column space is the dimension of the image. So if I'm asking for 1-to-1 and onto, knowing what the kernel is tells you whether it's 1-to-1 or not. Knowing what the image is will tell you whether it's onto or not. Feel free to ask questions if they occur to you, or maybe I can put it in the, if I don't know. I try to provide for shy people, so let me I open the chat. So if you put something in the chat, I'll see it, and I'll keep you anonymous or something. I don't know. All right, so here's a question 2. This is just about getting coordinates. So I give you a basis U1 and U2. And then I give you a V, capital V, a vector space. And I gave you 2 vectors whose B coordinates are known. They're 2, -1, and 3, 1. And I asked you to determine this linear combination of V, W, and one of those basis vectors. And what I want to see here is I want to see that you understand that this is a linear procedure. In other words, you can break this up into V plus 2W minus U1. You can break it up like this. Okay. Coordinates like that. And when you do that, you get, well, you know what V is. I say so here. You know what W is. So 2 times 3, 1. And you know what now here's where I'm asking, what is U1 with respect to B? So what is it?
1, 0.
Yeah, 1, 0. It's just the basis, the standard basis vector, because that's the first of them. The first of the basis vectors I've written down. Very good. So, okay, so then it's just arithmetic. So 2 plus 6 minus 1 is 7. And -1 minus, -1 plus 2 is 1. Okay, that's it. 20 points. Everyone's happy. Okay, 3. Yeah, solve a matrix equation. Okay. Let's do it. Why not? Life's too short. Maybe life is too short to do it, and not too short to not do it. But it's okay. We'll do it anyway, regardless of the length of life. All right. So first thing I'll do is okay, so again, row reduction does not have to follow a particular form, but I'm gonna just do a couple of things at once. I'll multiply row 2, and I generally don't advise people to do this, but I'll do it. I'll multiply by -1 for row 2, and then I'm going to switch row 2 and row 1. So I'll do it in that order, top to bottom. So I'll get 1 minus 2, 0. So this is a recipe for making mistakes, is what I'm doing. It's doing 2 things at once with the same row. But it's life. What do you want? Okay, 0. And I might as well, while I'm here, I won't do anything here. I'll just do this. Okay, great. Now I'll send row 2 minus 2 times row 1. I like to get my ones in, if I can, I like to bring the 1 to the pivot position. In other words, if I see something that's easily made a 1, I'm just going to put it in that pivot position. That way I can easily reduce the guys below it. All right, so -2, 0, nothing with this. And now I'm going to add -2 times the first. That's 4 minus 3. So that's nice. 4. And then I get -1 here. Okay, so now -2 plus 2 is 0. 0, -1, 1. Uh-oh. So we can already see some issues here. 1 minus 2, 0. -1, 0, 1. -1, 0. And here, okay, so I'm adding. I'm just doing this for fun. R3 plus R2. So, what do you guys think? Actually, this is okay. What should I do here? I guess I'm not completely done. Let's add 2 times R1 plus 2 times R2. 0, -2. Oops, not 0. This one. 0. 0. Okay, now not O. All right, so what do you think? So everyone's happy? Good. We've got 1 free variable, yeah. And if we want the solution, this is our free column. So let's just give a free variable t. And the solution is going to be x of t equals. So again, with the free variable is the third variable. So we'll put a t there. And then we get, using our standard solution, we'll get t here. And then we'll get 2t minus 1, or -1 plus 2t. This is just using this formula. Now, if you didn't see how I did that, that's okay. What you do is just put in the t, and then look at this. Look at these equations. So the first equation is going to be x1 plus. Or sorry, the first equation is x1 plus x. Sorry. This is the free variable t, the third. I'm going to put in the free variable t anytime I have a free column. So this is going to be x1 minus 2t equals -1. And the second equation is going to be x2 minus t equals 0. And so these two equations are giving me these two values. Just adding t or 2t to both sides give me those two solutions. Questions? That's the general solution. And it's the parametrized solution. If you want, you can kind of write this as kind of a linear combination where you take the constants. This is a totally not necessary, but I kind of like leaving it in this form if I can. And the reason is because we sort of get a basis for the span, for the linear space that's on. But you don't have to do this, not necessary. Oh, sorry. Okay, yeah. Great. So this is your, was this the one you asked about, Bowden? 4? Okay. Yeah, 4 is sort of the abstract kind of one. All right. So I gave you a linearly independent collection of vectors, and then I gave you an additional one. So this is some linearly independent set, and then I have one additional one, V. And I want you to say that one of two things happens. Either we get a linearly independent set by adding on this additional vector, or it's in the span. Okay. Okay, so how do you go about showing something like this? Here's the idea. So this is sort of a definition type problem. I want you to kind of pursue the definitions. Okay, so here's how I would start. So either V1, V2, up through Vn, and then V is linearly independent. In which case we are finished because we want to show it's one of two things, and this is one of them. In which case we're done. We are done. Or, this is going to really shock you guys, it is not. Okay. It is, I know. This is why I get paid the big bucks. When it is not linearly independent, it is called linearly dependent. So in the latter case, the case where we're not done, V1 through Vn and V are linearly dependent. And what that means, I mean, just following the definition, it means that there is a non-trivial linear relation. That is the definition of linear dependence. So that there is a non-trivial linear dependence. And let me write it out. A1 times B1 plus A2 times B2 plus ... plus AN times Bn plus the last vector, B times B equals the 0 vector. Because I've been dropping the vectors, but let me write the vectors here. Okay, this is non-trivial, meaning that not all of these are 0, right? If all of them are 0, that's the trivial relation. But if I'm saying they're it's non-trivial. So now what I want to say is I want to say B must not be 0. So I am not a shy kind of guy. If I want to say something, I say it. Note, B is not trivial, is non-zero. And then I'll explain myself afterwards. Because if it were, then we would have a non-trivial relation amongst the amongst the V's, V1 through Vn. A1 V1 plus A2 V2 plus dot 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 plus AN VN would equal 0, right? If this guy is 0, then this whole term is 0. And we're left with this relation. But we know this is nonlinear or non-trivial, so this would have to be non-trivial. In other words, what does that mean? We know that there are some that I said is linearly dependent, meaning there is a non-trivial linear dependence, which means that there is an equation like this, where some of these, at least one of these, must be a non-zero term, a non-zero scalar. If all of these coefficients are 0, that means it's a trivial linear relation. So I know that I'm saying it's non-trivial, so it's one of them, at least one must be non-zero. Well, if B is 0, then one of these other ones must be non-zero, and this is 0, which means that this is non-trivial, but we know these guys are linearly independent. So that can't happen. Because if it were, this would be a non-trivial relation amongst the V1 through Vn. But V1 through Vn are linearly independent by assumption. We assumed that. This can't happen. Thus, I verified what I asserted. B is not a zero scalar. But once B is not a zero scalar, we're in business, right? Because if B is not a zero scalar, that means, oh, I don't want to style that. That means I can take this relation, I can subtract BV from both sides. I can divide by negative B, because that's the key. Because B is non-zero, I can divide. When I divide, I get negative A1 over B, negative A2 over B, negative AN B. And look what just happened. We have that V is written as a linear combination of the V1 through Vn. So V is in the span of the other ones. We want to show. So we said, okay, let me summarize. We said one of two things happens. When we look at this set of vectors, either it's linearly independent, we're done, or it's not. If it's not linearly independent, then this collection of vectors here is dependent, which gives us a relation. Linear relation, non-trivial linear relation. We rule out the case of B being non-zero, or sorry, of B being 0 through this argument. We say, okay, if B is 0, then we have a linear relation amongst the V's, V sub 1s through V sub n. That's not allowed. So therefore, B must be non-zero, and we can divide by it, or divide by its negative, and we get that V is a linear combination of the vectors V1 through Vn. But that just means that V is in the span. We're done. Does it make sense?
Yeah, so this question isn't just asking to show either, it's to show that it has to be one or the other. Is that what it's saying?
Yes, it has to be one or the other.
Okay.
It is actually one or the other.
Okay.
So they're exclusive. Either is sort of, I mean, I don't know. When you're doing logic and math, it really depends. But often either could mean either, like it could like either or both. In this case, it's actually either exclusive. Okay. So Bo, this question is a beautiful question that we'll talk a little bit about, or you'll talk a little bit about tomorrow when you talk about the rank nullity theorem. Um, so, which I think, yeah, this is in this section. So what is the rank of? We have talked about the rank of T of a matrix and a linear transformation. So the rank of TA for A, sorry, rank. Sometimes it's written like this. Sometimes it's written out like rank. I mean, less commonly. You can write the matrix. When you talk about the rank of the matrix, it's the same as the rank of multiplying by that matrix. It's also the column, dimension of the column space, dimension of the row space, but it's also the number of pivots, which is what we saw before. So here, what you can do is you can just do some row reduction and see that, okay, so 0. I'm going to subtract 2. I'll get 0. I'll get -4. I'll get 3. I'm just reducing by taking R2 minus 2 R1, R3 minus 3 R1, 0 is 0, -4, 3. You can see that these two rows are the same. So just subtract one from the other and we get a row echelon form. Not reduced, but nobody minds. And we see that we have two pivots. So the rank equals numbers of pivots, number of pivots, pardon me, which is equal to 2. Okay, that's it. That's not a, that's a 0. Now, there is a theorem that we'll see tomorrow, which is the rank nullity theorem. And the rank nullity theorem is a really simple theorem. You'll never guess. Well, you maybe you wouldn't guess, but it's too simple for words. It says that the following. I mean, here's the decoding of it. So rank nullity is essentially, well, okay, so what does it say? It says if I have a linear transformation T from V to W, then the dimension of the image of T plus the dimension of the kernel of T is equal to the dimension of the vector space V. Now, this is a very abstract looking thing, but we're going to write it down in terms of matrices. So this linear transformation, TA, is multiplying by a particular matrix. So in that case, we have this, let's talk the matrix version of this. We have TA is from R4 to R3. So in this case, our V is R4. And we can say, okay, what is this equation, this is rank nullity, say about this particular linear transformation? Well, V is R4, so the dimension of V is 4. The dimension of the image is the rank of the matrix, rank of A. The dimension of the kernel is what's called the nullity. I don't remember. We write nullity or what will we write? There's different things. So this is the rank of A plus the nullity of A is 4. Now, what is the rank of A? It's the number of pivots. This is a number of basic columns. So in this case, I just did the row reduction up here. We have 2. So that's 2. So I have 2 plus the nullity equals 4. It's a hard equation to solve, but I know you all can do it. I believe in you. looking at the chat and nobody's saying anything. You can speak as well. It's okay.
Two.
Two, thank you. Thank you. It's just a check to make sure everyone's awake. I'm not. I'm hardly awake. Okay, good. Thank you. Nullity is 2. So this tells now why is the nullity? What's another reason the nullity 2 is 2 is we know that the number of parameters in our parametrization of the solution space is the number of free columns, which is really the dimension of the solution space, if that exists, if the solution space exists. So actually, another way you can say this theorem, so the answer here is 2. The answer here is also 2. Right, it's 2. But again, one explanation of this is that the nullity can be thought, it is also equal to something we understand, which is the number of free columns or number of free variables. So the nullity is the number of free variables. The rank is the number of basic variables. But if you add up the number of basic variables and the number of free variables, or number of basic columns and number of free columns, you get the total number of columns, which is in this case, this number, whatever this dimension is, because you're multiplying on the left. So this rank nullity is just saying, okay, if I add up all of those basic columns, the number of basic columns, and then I add up the number of free columns, I'll get 4. So that's it. So it's not a shocking theorem when you think of it that way, but it's actually very useful. It's extremely useful. You'd be surprised how often this kind of a question comes up. So it's kind of nice to know it. Okay, so that was fun. I think we have a little more time. I brought in, this is not my class on toric varieties, but for some reason I have the practice exams in here. The other exam. So were there any other questions about that about the last exam? The four was obviously is the kind of the hard one. I mean, so there might be a little bit of a harder one. I don't know, 4 is a little hard, but I want to throw in one challenge one to you guys about definitions, about some basic ideas. It may take you a minute. If it's not 4 in the exam I give you, it could be 2. I would recommend just coming back to it. Take care of the questions that are not the hard one first, and then give yourself some time to write some things. Tips for this kind of a problem, by the way. So maybe let me say this. So when you're taking a test on something where there's more math arguing, making some more argued points in a math exam where I'm asking you to justify something or give. One thing I like to see, I give a lot of partial credit. One thing I like to see when I give that partial credit is I like to see definitions. So if you don't know how to make the argument, but you do know what the terms mean, go ahead and write down what your understanding of those terms are. And that shows me, okay, well, you maybe missed some part of the logical argument, but you do know, you do know what's being talked about. So that's a tip. I really do give good partial credit for those types of things. And I'm not, I'm a very forgiving person when it comes to computational mistakes because I make my fair share of those. So I'm understanding. Okay, so as I said, try when you're looking at this first kind of problem, try it, a different sized matrix. So let me look at 2B. And again, 2B, just go ahead and row reduce. So here I'm just going to write it down. And again, I'm row reducing just the matrix. I'm not going to, so I'm going to subtract the first from the second. So I'll get 0, 2, 1 minus 4 is -3. And this is my row echelon form, right? So I have 2 pivots. which means I have two basic variables and I have one free variable. So rank, let me call this matrix A. Rank of A is equal to, by what we just talked about,
2.
2. Nullity, new term. I know that we'll talk about it tomorrow. You'll talk about it in your with Tin, by what we just talked about.
1.
1. Number of free variables. Okay, nullity is the definition of nullity for a matrix. It is exactly the dimension of the kernel of multiplying by that matrix. Meaning that the kernel is a line in this case. The kernel is a line, which means it's not 0. And so if it's not 0, this is not one-to-one. If the kernel is non-zero, is non-trivial, we have a non-one-to-one function. Because, I mean, think of it this way. If it's non-zero, that whole line is being sent to 0, sent to the 0 vector. That's the definition of the kernel. It's all of the vectors sent to the 0 vector. If it's not just 0 sent to the 0 vector, you have many, many points or vectors sent to the same image. So it's not one-to-one. So this means not one-to-one. This means what? This means that the dimension of the image is 2, which equals the dimension of the codomain. This means that the image of TA equals the codomain. So, which is equals R2. It's a so there's an argument there which says, and I think there's a lemma in the book that says a subspace of a space is proper if and only if the dimension is strictly smaller. So if the dimension, if you're in R3 and you have a 3-dimensional subspace, it's everything. You can't get it to be smaller because then you could kind of get a bigger basis. So this is saying that in fact this is onto. The image is equal to the codomain, which is equal to the range. I mean, the image and the range are the same thing. So this is onto. And you don't really have to tell me what the range is if it's onto. Does that make sense? So again, the key is in answering a question like the properties of the linear transformation, if they're one-to-one or onto, is row reduction and then identifying rank and nullity. That those two numbers will tell you everything you need to know about onto-ness or one-to-one-ness.
I'm sorry, we know it's onto because it's less than or equal to 2, because it's R2. Is that correct?
Yeah, so we know that if we look at T of R, the image of T, right? The image of T, this is going to be a subspace of the codomain of R2. All the vectors in the image, oh, sorry, this is a typo, by the way. This should have a Z, sorry. My bad, apologize for that. So anyway, but we take the image, it's going to be a subspace of R2. This is just saying it's a vector subspace. But the dimensions are the same. So in other words, it's a plane inside of inside of the plane. So there's only one plane inside the plane. It's the whole thing. So there should be, in the book, there should be some statement that says the following, some lemma, I believe, that says that if I have a subspace U of V, then dimension of U is less than the dimension of V if and only if U is not equal to V. In other words, those you can ask if you have a subspace if it's the whole thing by checking the dimension. If it's not the whole, if the only way it's not the whole thing is that that dimension is strictly smaller. But if it's equal, then they're the same. So here we have a dimension 2 space inside of a dimension 2 space. They're the same space. So we conclude this. Is it okay?
Yeah, that makes sense. Thank you.
Yeah, no, it's good. It's takes a minute to get your head around that argument, even these days. All right. What about A? A, I'm asking a very particular kind of a thing. I guess you could see A is not one-to-one. in a variety of ways. What do people, so I know Camilla's already explained to me why it's not one-to-one. So maybe someone else looking at this, do you have a sense as to why this is not one-to-one?
Is it just not because there's no z? Um, there's no just z component, z to the 1.
No, so let me give you an example, Bowden, of why. So if I took f of, let me call it g. So if I take g of z equaling z cubed, and I don't write this, but I write g is a function from reals to reals, which is what you see in calculus, you all know the graph of that looks like this, right? That's the graph of the cube of z cubed. This is actually one-to-one and onto. So it's not so much the form, although in this case you could make an argument that this is not the picture even in the reals. It's more, it has more to do with maybe finding a couple of points that go to the same point. So z cubed is something cubed, z squared is something squared. I think if you look at something like -1 cubed plus -1 squared, what do you get?
-1.
Yeah, 0 plus -1 is -1, yeah.
Yeah.
So f of -1 is -1, but also f of 0 -1, yeah? So these are, but -1 and 0 are different numbers. And so they go, but they go to the same values. So this is not one-to-one. And the point is that the typical, sorry, I'll move this up here. The typical graph for a cubic is something like this. That's the typical graph. And we're in sort of a case like that. We're in a case like that. And if this fails badly, this sort of horizontal line test, that one-to-one test that you have when you're going from R to R. Here I'm going from C to C. A horizontal line test is a little bit tricky. There's still kind of a notion there, but I don't want to think of it that way. I just rather put in some values. Now, the truth is, if you have any, so now maybe Bowden, you were thinking something which is true, which is if you have any polynomial that is higher degree than 1, it is not, and you're considering it on C, it's not one-to-one. That's true. That's just a general true thing. I'm not going to try to prove that, but that's a true thing. What about onto? Onto, I love this question for the onto part. Because the onto part is kind of, you could, well, what do you think? Is it onto? F is a function from C to C. The answer is it is onto. Because how do I need to, let's take some value. Let's call it lambda because we're fancy and we want to call it some Greek letter. And I want to find a solution to f of z equals lambda, right? That's what, if I can find a solution to this, if I know a solution exists to that, that's onto. That's saying that I can put in that value into f and I get that value lambda. So every value is hit, is what I'm saying. But this equation, solving that equation is the same, I think you'll agree, as solving this equation. Does everyone agree? I see all your heads are nodding. That's good. I hope. Nice. Nice. Thank you both. It's taking me, I'm having flashbacks of COVID. I even teach online some things, so it's not even that bad, but it's asynchronous, so I don't know. This is different. Been a while. All right, anyway, so however, this is a cubic polynomial, and the coefficients are complex numbers, right?
Right.
So we have 1, 1, and this complex number, whatever it is. And there's this thing called the fundamental theorem of algebra, which tells us, and we didn't prove it, but we did state it. It tells us there always exists a solution to this equation. It says any polynomial equation with complex coefficients has at least one solution in complex numbers. So there is a solution to this by the fundamental theorem of algebra. Solution exists, which means that this function is on 2. And indeed, any polynomial, any non-constant polynomial is on 2, which is cool. Okay. So that's on 2. So it is on 2, not 1-to-1. I did one already like 2, so I'm going to skip 2. I also did one like 3. And I will tell you, I'll admit it fully without shame that I use my program to generate these kinds of problems because I know it'll generate something that has nice solutions. And I don't want to give you guys a headache, especially in an exam. So I look for problems with nice solutions. I hope that doesn't spoil you and make you think that everything has a nice solution. Fractions definitely are a part of life, but I'm not trying to test your arithmetic with fractions.
Just one real quick question, looking at reducing this one.
Uh-huh.
If we do an augmented matrix, does the like augmented row, does that would that count as a pivot, or is that like
A good question. So the answer is, okay, so the reduction of this matrix, right? So what are you going to get? Maybe we should just look at it. But just to answer, I'll answer your question once we get there. I'm going to switch these guys, and then I'm going to add 2 times this. I should have switched over here. So now, okay, I don't want to do that. I'm going to add 2 times the second row to what was the second row. I get 0, 0, and I get 2 here, right? Excuse me. This is, okay, this is the reduced echelon form of the augmented matrix. However, if you're talking about solutions to the equation, there's a step 1, and then there's a step 2, and then there's a step 3. That's all the steps. Step 1 is, does a solution exist? And
it doesn't because 0, 0, 0 equals 2.
right.
Okay, cool.
So no solution. And then you don't need to talk about free variables or anything like that. But if it passed that test and you did get a 0 here, then you're not going to have, it's going to be a moot point. There aren't going to be any pivots over there, but you don't really want to think of them. You want to think about the variables only occurring over here, free and basic. This is sort of a value. So you would kind of disregard it. Yep. Okay. So no solution because, and then Bowden's argument is what I'd love to see is, because something like, 0 equals 2 is not possible. So something like that. That's fine. Or you can say by theorem in the book or whatever you want. Okay, let's come back to this. Is there anything fun? Yeah, so here's a fun one too. Who doesn't love a little bit? So let's do the rank nullity again. Again, we have a 4x4. You can row reduce this to see that you get a row echelon form that looks like this, I mean, this is what you'll get after a little bit of manipulation. Which means you have, again, I promise the answer for the test won't be 2 and 2, like these are both, but you have 2 free variables. They're different, and you have 2 basic variables. So the rank equals 2, nullity equals 2. You're counting free and basic variables. Okay?
When
This question, oh, sorry, go ahead.
sorry, when looking for the rank, is it fine to leave it in reduced row, or sorry, in row echelon form, or should we put it into reduced row echelon form?
If you just need the rank, you're just looking for the number of pivots.
Okay.
Number of leading coefficients for pivots. So you don't really need to do anything further than row echelon form.
Okay.
It's unnecessary. This kind of a problem is really just about linearity and definitions. So here's what you would say. All right, so we'll say, I'll just do a bunch of an if and only if argument. Okay, so T of V1 through T of Vn is linearly independent if and only if whenever we have a linear combination of these vectors and these coefficients that implies that all of the A's are 0. Which is true. Oh, I gotta use my notability. If and only if. Save a little time in life. I'm just going to do the same statement, but I'm going to use linearity of T. Linearity of T tells me something like this. Right? If I just put in, this is just using linearity of T, I can bring all the A's in and I can take T of a sum of T's equals T of the sum. So that just makes this the same. But that's saying if and only if, I'm going to say this and then explain, the kernel of T equals 0. Now, why is this true? Because V1 through Vn is a basis. And every V in V is uniquely represented, uniquely written as a linear combination A1 V1 plus A and Vn. So what is this saying? What I'm saying here is that if I have any V in V, I can write it like that, which means that any V in V can be put in here as such a linear combination. But if when I put that V in here, I get 0, then all of those coefficients must be 0 and V must be 0. In other words, the only thing that is sent to 0 under T is 0. And that's exactly what this is saying. The kernel of T is 0. So this is just using the fact that this is a basis. So every single V has a representation like this. And this is saying if V is in the kernel, or if V is in the kernel, then V must have been 0 in the first place. Okay, great. And conversely, if the kernel T is 0, then anything you put in must actually be 0. anything you put into T and get 0, it must have actually been 0. Okay. But the kernel of T equaling 0 is true if and only if T is 1-to-1. That's what I'm being asked to show you. Good. I think that's where I was headed. This is an argument that every step is sort of equivalent to the next. That means that this is equivalent to this, which is what you're trying to show. But the key is, okay, you're using definitions. This is just definitional. This is linearity. And this is the argument involving a basis. What is a basis? And then this is a theorem in the book. And you can just say, you can say things like this freely. If it's a theorem in the book, you can refer to it. You can, I'll understand that you know it's something they're using. Okay, so this is a little bit tricky. It's a little hard, but even if you just make it up to the linearity bit, I mean, the hard part is maybe the basis issue, but if you make it basically there, I'm very happy. Okay. All right, I'm at about an hour and I'm turning into a pumpkin. So I think I'm gonna get off and let you guys enjoy the rest of your evenings. But thanks for showing up and I'll see you guys Friday.
Thank you.
Thank you.
you. Have a good night.
Yeah.